All right, so here's theorem 2.2. So this is the relationship between one-sided limits and two-sided limits, and we kind of alluded to this in the last example or slide. So basically, the limit as x approaches a, or the limit of f of x as x approaches a, equals L, right? Some value L, if and only if both these things are true. So if and only if the limit from the left equals L and the limit from the right side also equals L. Okay, so a two-sided limit only exists if the limit from the left is equal to the limit from the right. Okay, and then whatever that value is that they equal, that's what value the two-sided limit will equal. Okay, so if you're trying to find a two-sided limit, a lot of times what you do is you find the one-sided limit on either side and see if they're the same, and if they are, then whatever that value is will be also the two-sided limit. Okay, if they're not the same, that's when you get a DNE, or does not exist, right? So else, right, or else, if they're not true, right, if the limit as x approaches a from the left of f of x does not equal the limit as x approaches a from the right of f of x, then that means you're going to get that yields a DNE, does not exist. Okay, or remember, you can also use the backwards E with the slash. Okay, all right. So let's look at this example here. So here's a graphical example, and so we'll do I'll do two, and then I'll let you do one. Okay. So, and you're like, thank you, Mr. Gloy. Thank you for letting us do that. So, and you're welcome. You're welcome. And so, what we'll start with is the limit as x approaches 0. Okay. So here's where 0 is, right? So we'll do this. And so, as I approach 0 from the left, okay. As I approach 0 from the left here, I would follow this line. You don't have to start from way back there, but here's where it gets interesting, right? Is as we get closer and closer to 0, we want to see what's our output approaching, and it looks like our output is approaching 2, right? So the limit as x approaches 0 from the left is 2. The output is 2. So let's go from the right. So from the right, I would follow this function up, and it also looks to be approaching 2. As I get closer to 0 on the left, my output is 2. Okay. All right. So those are the same, right? Because these are the same, that means that this is also going to be 2. Okay. All right. Now I threw in this last thing, and this is something that we've done way back into algebra 1, which is function notation, right? So here it's saying find f of 0. So f of 0 is just what is the function at that point, right? If you just plug in 0 to the function, what do you get as your output? Now the issue here is at x equals 0, there's an open circle, and there's no closed circle anywhere else, right? Like if I scan along this x equals 0 line, there's no closed dot, right? There's no circle, or there's no point at that point. And so this would actually be undefined. Okay? All right, so the limit exists, but the function itself is actually undefined at that point. And that's one of the useful things about a limit, is we can find values that are we can find values that are undefined. Otherwise, we can't just plug in a point, but we can actually find what they approach, which, remember, is important. If we go back to average rate of change, if we're trying to approximate the tangent line and we get really, really close to that point, that means our denominator is going to be really, really close to 0. We can't just plug in 0, right, because we can't divide by 0, but we can find instantaneous rate of change by using actually a limit and getting super, super close to 0. So that's that connection between average rate of change and converting it to instantaneous rate of changes. We need limits to do that, because we'll end up with an undefined value if we just plug it in. Okay. All right, now let's check out this next one here. So let's look at this one. Okay, so now we're looking at where x approaches 1. Okay, and so let's start on the left. So as x approaches 1 from the left, I'm following this function, this graph, and as I get closer and closer to 1, it looks like my output is getting closer and closer to -1. So this will be -1 here. Okay. All right. Let's go from the right side. If I approach from the right, okay, then I would follow this function on the right side of 1, and as I get closer and closer to 1 on the x-axis, my output looks to be 0, right? Okay. So because these do not match up, because these are not the same, that means that this limit does not exist, right? All right. So, and then finally they're asking for f of 1. So at when x equals 1 here, what is the what is the output? And so if I scan along here, I see there's a point right here, which happens to be at x equals 2. So actually 2 is the answer for f of 1, right? So this is an interesting situation where we have a limit from the left that was not the same as the limit from the right. Okay, this limit from the left was not the same as the limit from the right. And so, which means that the limit does not exist, the two-sided limit does not exist. But the function does have a value at 2, right, which is different from either one of these. So that's kind of interesting. So we kind of got different values for all 4 of those. All right, so now I want you to try this out with the limit as x approaches 3, okay? So I want you to find the limit as x approaches 3 from the left, the limit as x approaches 3 from the right, the limit as x approaches 3, the two-sided limit, and then the value of the actual function at that point. So look for that closed circle, okay? So you're looking where x approaches 3. All right, so try that out. All right, so now we know how to find one-sided and two-sided limits using a graphical representation like we just did. We know how to use it doing tables, even though we didn't know about one-sided limits at the time. We actually found them, right? So we can just make a table and get closer and closer to the value from the left, as we did here, closer and closer to the value from the right, as we did here. And then we also know, and we can do that with any type of function, whether it be here we have kind of an absolute value rational hybrid. Here we have a piecewise function, right? And so those are the ways we can do it, is computationally by plugging in values. Sometimes if we have a piecewise function, or we can do a table by getting closer and closer and closer to certain points from the left or the right, and then or we can do it graphically by just kind of visualizing and following that curve as we get closer and closer to certain points from the left or the right. All right, well, thank you for joining me in this video virtually, and I look forward to seeing you in class. And definitely bring your please bring your questions and get ready to practice on these.